All right, hello, and welcome to section 3.2. So following the general trend of the course as we have in the past, in this section we're just going to go over some nice properties of determinants. Specifically here, we're going to sort of the main purpose of this lecture is to come up with a useful way of finding a determinant, which is easier than the sort of initial way that you found it. Sort of like, how a lot of math classes, I remember calculus went like that, where you, like you learned the very hard way to calculate a derivative, and then, oh, surprise, there's all these easier ways. It's going to be a little like that. Sorry. So, we saw this property actually at the end of last section with an example. I sort of mentioned it was going to foreshadow something that was going to happen this section. And so this property is actually given in section 3.1, but it seemed like it made more sense to state it here. And so what this says is that if I've got an upper or lower triangular matrix, then the determinant of that matrix is actually just the product of the diagonal entries on the matrix. So as an example, notice that we can verify this matrix is in fact an upper triangular matrix because it's got the lower triangle of zeros underneath the diagonal. This means that its determinant is equal to just the product of the three diagonal entries. And so I also want to make a quick note here, which I also made. Remember that we will often denote the determinant of a matrix by using straight line brackets like this. So this is to denote the determinant of this matrix, which by property 1 is equal to 3 times 2 times 4, which is equal to 24. That was much easier than doing it the way we learned initially in section 3.1. So, of course, this type of a trick is only going to work if you have, type of a trick is only going to work if you have an upper triangular matrix. And so, it'd be natural to look at this and say, well, this isn't going to be very helpful. But it turns out this is very helpful because one thing we have not discussed, I know everyone was missing row reduction, is how determinants and row reduction work together. Because remember, we can always row reduce a matrix to an upper triangular matrix, right? That's basically just the process of reducing it to a row echelon form. But notice that, so because of this, if we can find some nice relationship between how the determinant and row reduction steps work together, then we might have a slightly quicker way, especially with matrices of higher order, of calculating determinants. And so it turns out there are some very nice properties about how determinants and row reduction steps work together. And so what I want to do is state these steps, and then we will see sort of how we can use these on a 2x2 matrix, and then we will actually just end by seeing how we can use them on a 3x3 matrix in a very, very nice way then of sort of finding determinants in some cases. So we're going to let A be a square matrix. Again, remember that means n by n matrix. And we get the following 3 properties. So if a matrix B is obtained from A by performing a row swap, then the determinant of B is just equal to negative determinant of A. So if B is obtained from A by performing a row swap, the new matrix I got will just be the negative of the determinant of my old matrix. And so if I perform a row swap, and I want to know the determinant of the new matrix, I don't have to do that much work. 2, if B is obtained from A, after adding a multiple of one row to another, then the determinant of B is actually just equal to the determinant of A. So it turns out that the row operation of replacement, right, which is sort of the most used row operation that we do when we're transforming a matrix, this doesn't even change the determinant. Okay, well, lastly, if B is obtained from A, after multiplying a row by k, so this is where we multiply a row by some scalar, then the determinant of B is equal to k times the determinant of A. So we've got all three of our row operations. We know how all three of the row operations change the determinant of a matrix. And this is huge because this means if I take a matrix and row reduce it to some upper triangular matrix, all I need to do is work backwards, keep track of the row operations I used to transform that matrix, and I can calculate the determinant of my original matrix. So what I want to do, I found a nice example where I can use each one of these row operations exactly once. And so I want to sort of give the row operations I used. We can calculate the determinants at each step, and then explain how we could actually have worked backwards if we didn't immediately know the determinant of the starting matrix. So the matrix we're going to use is the matrix 3, 4, 1, 2. And what I'm going to do is write the determinant of each matrix in blue underneath that matrix. So notice, since this is a 2 by 2, the determinant is equal to 6 minus 4, which is equal to 2. And so that's the determinant. All right, so the first row operation I want to do, well, I'd like to put a 1 here. So I'm going to swap row 1 and row 2. All right, well, so that gets me my favorite matrix, 1, 2, 3, 4. I don't know if I'd say that's my favorite, but for some reason it's always the first example I can think of. So calculating the determinant normally, well, this is equal to 4 minus 6, which is equal to negative 2, which is very good because by property 1, it says, well, the determinant of this matrix should have been the negative of the determinant of this matrix. All right, so next I'm going to do negative 3 row 1 plus row 2. Get me 1, 2, 0, negative 2. And look at that. This is already an upper triangular matrix. So I actually don't have to go further. I'm going to just for the fun of it. But notice here, the determinant is equal to 1 times negative 2. And so this row operation actually hasn't changed a thing. All right, now let's say I wanted to put a 1 here. I could do negative 1/2 times row 2. I get 1, 2, 0, 1. And so here the determinant is equal to 1. And so notice with this, if I wanted to work my way backwards here, right, I know that the determinant of this matrix, right, is equal to negative 1/2 the determinant of this matrix. So let's pretend that I lived in a world where I only knew the determinant of my ending matrix. So I got here, I calculated the determinant was 1. Well, because I did negative 1/2 times row 2, I just want to multiply by the reciprocal of that. And so I want to multiply by negative 2. And so that gets me a determinant here of negative 2. I did a row operation, so I won't do anything there. Here I did a row swap, so I know these determinants should be negatives of each other, or times negative 1. And I work my way all the way back to the determinant of the original matrix. So notice, doing these row operations, if I can get it down to an upper triangular matrix, I can just work my way back by keeping track of all of the row operations I used and find the determinant of the original matrix. So I think I accidentally gave away the punchline here. We didn't even need this last step, right? I had mentioned this matrix is already upper triangular. And so I claim that if you have a 3x3 matrix, you can actually row reduce it to an upper triangular row echelon matrix just by using only steps 1 and 2. That is, only using row swaps and multiples of things. So this means that in this instance, I could have stopped here, right? Because I have an upper triangular matrix. I just multiply its diagonal entries to get a determinant of negative 2. And since the operation 2, since adding a multiple of a row to another doesn't actually change the determinant, the only thing I need to check when I get to this ending step is how many row swaps did I do. So what we're going to do is we're now going to do an example where we row reduce a matrix, and we'll keep track of the number of row swaps we use. And then what we do is we just basically multiply by negative 1 the number of times we did a row swap, and that'll calculate our determinant. And this will give us a new, very nice way of finding the determinant, which will prove to be very useful. All right, so we're going to do a 3x3 matrix now. And so we want to find the determinant of, and so our goal here, even though it might be nice to use a row scaling operation at one point or another, is to not use any row scaling operations. Of course you still can, right? You'll still get the correct answer. It ends up being a little more work, and ends up being a little more work and a little more chance for error because it's kind of the harder one to keep track of, right? Row swaps, you just have to keep track of the number of row swaps, then multiply by negative 1 that many times. So anyways, all right, so using our new tools, we're going to row reduce this. So first thing I'm going to do is negative row 1 plus row 2. All right, and so again, here would be sort of the step. It would be tempting to divide out 3 here, but I'm actually not going to. I'm just going to multiply 2/3 or negative 2/3 row 1 plus row 3. And that'll get me the following matrix. So that is 0, -4, yeah, -4, and let's see, 2 plus 5 is -3. Oop. Okay, and so then I want to do 4 times row 2 plus row 3. That's 3, 3, -3, 0, 1, -1, 0, 0, -7. All right, and so at this point, I have row reduced this matrix to an upper triangular matrix. Again, I've got the triangle of zeros there. And so notice now what's going to happen. Well, I can calculate the determinant of this matrix by just multiplying the diagonal entries. All right, and now, okay, I know the determinant of the echelon form. Did I ever use a row swap here? Well, no. So this means that the determinant of my original matrix is also -21, and that's my final answer. So without having to use any sort of cofactor expansion, I didn't have any zeros there, just a few simple row reduction steps, and I was able to find the determinant. All right. So I'm going to now just briefly outline what we did and sort of how you can, in general, find the determinant of a matrix sort of using these tools. All right, so I think this is the fancy, new, useful way, no, very useful, new, fancy way of finding a determinant, which is very useful. I won't write all that on the board, but how to find determinant of A. And so what's sort of nice or interesting about this is that this is one of those things where there's never going to be one correct way to do it. Because in some cases this will be easier, but in some cases cofactor expansion will be easier. Specifically if you do have a lot of zeros on a matrix. Right, cofactor expansion can still be fairly straightforward, but this can help for larger matrices where you don't have that nice row or column to expand over. So find determinant of B, and again here 2 is made easier because this is just the product of diagonal entries. So next, let K equal the number of row swaps you used. And so notice here, K is anything between 0 and whatever. Probably wouldn't be, I guess if you wanted to, you could make it pretty big, but it could be 0. And so then we know that the determinant of A is equal to -1 to the K times the determinant of B. And so this is the big punchline of this lecture. If you can row reduce A to an upper triangular matrix, all you have to do is keep track of the number of row swaps you used. And maybe I'll put here not using scaling, right? Because you have to row reduce it to an upper triangular matrix without using any scaling operations. But if you can do that, again, not using scaling, all you have to do is keep track of the number of row swaps you used, and we've got our determinant. But again, keep in mind, no scaling operations. So this only works if you do not use scaling.